Find the natural frequency of the system shown in figure and show that the natural frequency is equals to omega n equals to square root of 2k by 3m, where k is the stiffness and m is the mass of the system. So the system that is given is this disk of mass m and radius r is connected through a spring to a surface, and this is a rigid surface. Now this disk rolls without slipping. That is the assumption. So let's assume that this is going to roll at distance x. Okay. So we want to show that omega n is equals to square root of 2k by 3m. We'll solve this problem using energy method as well as Newton's second law of motion. So let's first start with energy method. According to this, the total change of energy is going to remain constant, okay, or zero. So d by dt of potential plus kinetic energy will be equals to 0. So let's try to find the kinetic energy. The kinetic energy will be equals to translational plus rotational. Okay, so translational is half mv square or half mx dot square in our case, plus rotational is equals to half, instead of m you have got j0 and instead of x you have got theta 0 square. So this is the rotational kinetic energy. So you can replace the x with respect to theta now. Let's assume that this is going to roll with an angle theta. Okay, so suppose this is angle theta. So what you have is half m this angle in the inset is theta, so x will be equals to r theta, very simply. And in this expression you can replace x dot with respect to with r theta dot square plus half j0 in this case is that of a cylinder or a disc. Okay, so j0 is half mr square times theta dot square. The spring is assumed massless in this case, so you'll end up with 3 by 4 m r square theta dot square. That's the kinetic energy in the system. The potential energy is the energy stored in the spring. Okay, so let's go to the spring. The potential energy will be equals to V is equals to half kx square. Okay, so x can be replaced by r theta, so half k r square theta square. Now d by dt of t plus v equals to 0. So this is equals to d by dt of t is 3 over 4 mr square theta, sorry, okay, so half 3 by 4 mr square, then what you have is theta square plus half k r square theta square. Okay, and this whole thing will be equals to 0 according to the law of conservation of energy. So this thing is can be written as 3 by 4 again. Mr square will be constant. Okay, now theta square can be written as 2 into theta dot, that's the derivative, times theta double dot plus 1 by 2 kr square is constant with respect to dt, and again this will be 2 theta times theta dot. Okay, this whole thing is equals to 0, so you will end up with okay, so in this case now theta dot can be taken out common, and you know that theta dot is not equals to 0. So using that you can easily find 3 over 2 m theta double dot plus k times theta equals to 0. So this gets cancelled, right? And then 2 gets cancelled, even r square, this becomes 2. So you will end up with this expression. Okay. This is the characteristic equation of our system, and very simply you can find the omega n as equals to, from this, just by comparing with the characteristic equation you will find that omega n is equals to square root of 2k by 3m from this expression. Okay, so this is the required answer. Now we can solve the same problem using Newton's second law of motion or equation of motion. What we'll do is we'll first establish the solution methodology. Okay, so you know that in this case some of the moments, Newton's second law we are solving now. Newton's second law, sum of the moments is equals to J0 times theta double dot. Okay, in our case the basically J0 term can be written as equals to, now we need to find the J0, which is the moment of inertia at the oscillation point. So suppose this is the disc or the cylinder, right? And this is the radius of r. Okay, and this is going to travel distance x, right? And this will have a force basically from the spring which will be pulling it in the other direction. That force will be equals to kx, and the point of rolling or the point of oscillation is O. Okay, so J0 at the center you know is equals to half mr square, but if you want to transfer it to the point of rolling or the point of oscillation, then you have to consider the distance r, right? So then you can use the parallel axis theorem and then transfer it mr square. So this is the entire expression for J0 in this case. The moments what you'll get is again there's only one force, which is the spring force, right? So the spring force is then equals to kx. Okay, so kx times r is the spring force. So r is the moment arm in this case. So kx is the spring force times r will give the moments, right? And again, since this is in clockwise direction, so this will be negative, right? So if you put this together, you will end up with this term as equals to 3 over 2 mr square. So what you have is 3 over 2 mr square theta double dot plus kr square theta equals to 0. Again, this is the same expression or equation for characteristic equation of motion, right? So similar to the energy method, these two are the same. So you'll end up with omega n just by comparison as 2k by 3m. So comparing this equation with the characteristic equation, that is x double dot plus omega n square x equals to 0. So from comparison purpose, by comparing, you will find that omega n square equals to 2k by 3m. And again, this is the solution that is needed. So we solve the same problem using energy method as well as equation of motion. Okay, thank you.